Hello everyone, welcome to lecture number 3 of this week, fourth week. We have already seen that comparison test in the first lecture of this week. The second one include Cauchy root test. In the comparison test, we have compared two series to investigate their convergence, right? So if the convergence or divergence of a series is unknown, then we forced another series which convergence or divergence known to us. And once we have then compared term by term, and then we have three theorems, the first type, second type of comparison test, and the last one was the limit form comparison test, by which we conclude that series is convergent or divergent, right? In the second lectures, we have explored Cauchy root test. So if a series containing the terms in a power or something roots or surds or indices, then in such cases we directly use Cauchy root test. And for the Cauchy root test, we have only calculated one limit, that is limit n tends to infinity un to power 1 by n. If that limit is less than 1, the whole series is going to be convergent. If the limit is greater than 1, the whole series is going to be divergent. But we don't know, or the test fails when limit become 1. Now in this real numbers ratio test, which is quite basic and very frequently used to test or to investigate convergence of a given series. As the name suggests, the ratio test, that means I am going to find out one limit only, the ratio of the two terms of a given series, and with that limit I will conclude, or we are going to conclude that the whole series the convergence and divergence of the whole series depends on that limit itself. So here is the statement, as you can see here, that un be a positive term series, and then if limit n tends to infinity un plus 1 divided by un equal to L, then the series is converges if L is less than 1 and diverges if L is greater than 1, and test fail if L equal to 1. Now I am going to give you the proof, outline of the proof, and you will follow it very quickly, that this is the same type of proof as we have used in a Cauchy root test. So what it is given? It is given limit n tends to infinity un plus 1 divided by un, that is L. So by definition itself, we have un plus 1 by un minus L modulus is less than epsilon for given n is greater than equal to m, and m is a natural number. So for a fixed natural number m, we have this criteria. That means we can explore this one, and we have L minus epsilon is less than un plus 1 divided by un is less than L plus epsilon, right? And this is true for every n which is greater than and equal to m. Remember this one, and you can classify this things, because this will give you criteria where you can use directly the previous approach to prove that theorem. So for case 1, where we have L is less than 1, and we are going to prove that if it is happens, then the series is convergent. Let us choose a positive epsilon such that L plus epsilon, so I am going to use this one. So L plus epsilon is equal to some number r, and which is less than 1, right? So we have here 0 to 1, so 0 to 1, and L is less than 1, so L is less than 1 here, and then L plus epsilon is also less than 1. Now this will we have found from here. So L plus epsilon equal to r, then this L plus epsilon lying between 0 to 1, right? So each r has the lower bound as a 0 and the upper bound as a 1. Now continue with the same processes. So we have L minus epsilon is less than un plus 1 divided by un is less than L plus epsilon, and this will happen for every n is greater than m. So L plus epsilon equal to r, so I can write this one as un plus 1 by un is less than r, and this will happen for every n is greater than m. So choosing n is greater than m, what does it mean? That means we have m plus 1, m plus 2, m plus 3, and how many terms we have? We have n, right? So that means um plus 1 is less than r, plus 2 divided by plus 1 is r, and so on. So I mean cancel out the middle terms or intermediate terms. What you will get? You will get un divided by right, by taking the product of the each side of this inequality. You will find out that r is less than n minus m, and remember r is what? R is less than 1. So hence I can have this each term un is less than divided by r power m into rn. So this is the fixed quantity. So un is less than something, un is less than some fixed quantity k into r power n. So if I knew the Rn is what? Rn is a geometrical series where the ratio r has the less than 1, and that means the series is going to be convergence series, and henceforth by comparison first test here. And now you can look at why comparison first and second test has been explored before the D-L'Alembert ratio test, because that was the base where we can use those things to prove this D-L'Alembert ratio test and so on other test. So that will give you, by comparison first test, that will give you the whole series is going to be a convergence series. Now look at the case 2 where you have a limit is L is greater than 1. To prove this one, since limit is already greater than 1, therefore if I subtract a very arbitrary, very small number epsilon, it does not hinders its quality, right? So L minus epsilon is greater than 1 still, and now put this value L minus epsilon as something p which is greater than 1 here, and use those inequality, because I mean limiting values property, because limit n tends to infinity un plus 1 divided by un equal to L is given. Therefore very small epsilon is greater than 0. There exists a number, positive number k, such that L minus epsilon and is less than un plus 1 by un is less than L plus epsilon for all n is greater than or equal to k. Now use the left hand side of that inequality. So the inequality says, I am writing here for you, inequality say L minus epsilon is less than un plus 1 divided by un, and L minus epsilon is nothing but p. So p is less than un plus 1 divided by un, right? So un plus 1 divided by un. So that means for p is greater than 1, for p is greater than 1, un divided by uk, right, is greater than p n minus k. And exploring this inequality, un is greater than okay, so un is less than uk divided by p of n minus k, and again you will have un is less than uk divided by pk into of pn. This is not r, this is p, right? So this is something un is less than uk divided by pk into pr, right, for each n is greater than k, right? And this is a fixed quantity, this is a fixed quantity. So again we have the same thing, and since Pn is a geometrical series and P is greater than 1, henceforth it is a divergence series. It is a divergence series which leads that by first comparison test the series un is divergent in that case. So we have discussed two cases where L is less than 1. The first comparison test leads that series is going to be converging series. and L is greater than 1, where also first comparison test leads that UN is going to be diverging series, right? But we cannot conclude anything about L equal to 1. So, if the limit value of limit UN plus 1 divided by UN is equal to 1, then the test fails and there is no conclusion at all. How we can do this? So, in that case where you do not have to prove that mathematically, you need some counter examples. So, I will give you the two counter examples where in one the limit value is 1 and the series is going to be convergent. Another one where the limit is 1 remain the 1, but that series is divergent, and that makes that this test is not going to work there. So, consider the two series as a series 1 by n and series 1 by n square. Look at the limit first. So, limit of un plus 1 divided by un in the first case, what will happen? You have a limit of n tends to infinity 1 divided by n plus 1 divided by 1 by n. So, this will give you n divided by n plus 1, limit of n tends to infinity, this will be 1. Similarly, you can find out for the second limit, limit is the sum 1. And now this series summation 1 by n is a diverging series, and this series is a convergent series as a P series, right. So, we have proved this theorem by taking each cases individually. In the first case, we have chosen L is less than 1 and L plus epsilon is equal to some R, where we will find out that since it is R is less than 1, the geometrical series is a converging series, and henceforth by comparison test is a converging. And in the second one, where we have discussed about L is greater than 1 and we have chosen L minus epsilon is P, and which is greater than 1, still it is greater than 1. So, therefore, we have conclude that the series geometrical series is a diverging series, leads that series is diverging. And here for L equal to 1, we have given two counter examples, that series 1 by n which is a diverging series and series 1 by n square is a converging series, and both have the limit L equal to 1. Henceforth, test does not work and test fails here, right. Now, can I use this D-Elmers ratio test to test or investigate the convergence of a given series of the positive term series? Obviously, yes, and this is very frequently used. So, you have for a given series, you have to start from the D-Elmers ratio test. If the terms does not contain power and sorts or indices, then you have to start with the D-Elmers ratio test first, and if it fails, then the further tests are also available to do this, right. So, look at the series. Series is given summation n square minus 1 divided by n square plus 1 into xn, and x is a variable which is greater than 0. So, for a positive x, we have a series whose terms a n or un is n square minus 1 divided by n square plus 1 into x to the power n. That's good question. So, firstly, I have to find out the ratio between un plus 1 by and un, and what it happens, it will comes out to be, and take the limit both sides. So, limit n tends to infinity, it will comes out x. Now, this x define the series is converges or diverges depending on the value. So, if x is less than 1, by D-Elmers ratio test, the whole series un is converging. If x is greater than 1, the whole series un is diverging, and if x equal to 1, test fails. In that case, you have to put the value of x in the series. So, what the series becomes? Series become n square minus 1 divided by n square plus 1 into 1 to the power n. So, this will be also series summation of n square minus 1 divided by n square plus 1. Now you can have the test to test this is converging and diverging. How to test this? So let put limit of 1 minus of 1 n square divided by 1 plus of 1 by n square. So this will comes out to be limit un, limit n tends to infinity un is equal to 1, which is not equal to 0, right? So you cannot use the basic theorem where a series is converging. That means you can use the basic theorem here that this series is not converging, right? So at the end you have to conclude that this series un is convergent when x is less than 1 and divergent when x is greater than or equal to 1. That's their answer. The next question, look at the structure of the problem. It says that test for the convergence of the series 1 square, 2 square, x1, 3 square, x2. So you can write this one as 1 square into x to the power 0 plus of twice square into x to the power 1 plus of 3 square into x square plus of 4 square into x cube and plus so on. So what is the un? Un become n square, right? Look at this the third term. So n square into x to the power n minus 1, right? That is the un. So we will find out un plus 1 is equal to n plus 1 ka whole square into x to the power n. So henceforth un plus 1 by un, taking the limit n tends to infinity. Calculate this. This will comes out to be limit n tends to infinity, and see here xn and xn minus 1 is cancelled out. So it will be coming out 1 plus of 1 by n ka whole square into x, and that will give you, this is going to be 1. So this will going to be x, right? So that means we have limiting the ratio by ratio test. We are going to conclude that the series is convergence when x is less than 1. This is the series is converging. Summation un convergent if this happen, and this is divergent if x is greater than 1, and test fall when x equal to 1, test fails. Now you have to put this x equal to 1 in the series itself. So what it become? It become 1 square plus 2 square plus of 3 square plus of 4 square plus of so on. What do you think? That the series is convergent or divergent? Look at the structure and you will find out that the series is not a converging series, it is a diverging series, right? So now come to the next question, that is test the convergence for the series x divided by 1 into 2 plus x square divided by 3 into 4 plus of x cube divided by 4 into 5 plus of and so on. Not only 4 into 5 but 5 into 6, right? And so on. So that means un can be written as x to the power n divided by 2n minus 1 into 2n, right? Look at the second term, look at the third term. This is the same thing, right? So how to do this? So find out un plus 1 and then take the ratio un plus 1 divided by un and take the limit n tends to infinity. It will comes out, do the calculations. I mean I can do the calculation for you if you need. So this will comes out to be xn plus 1 divided by 2n plus 1 into 2n plus 2 into 2n minus 1 into 2n divided by xn, right? So these two will comes out to be limit n tends to infinity. This is x, right? And this will comes out to be 2n minus 1 into 2n divided by 2n plus 1 into 2n plus 2. So taking the limit in here, so this will comes out to be limit n tends to infinity x into 2 minus of 1 by n into 2 by n divided by 2 plus of 2 by n into 1, right, and into 2 plus of 1 by n. So all these cancel out and it will comes out directly to x. Let's come to x. So by D'Alembert ratio test, if x is less than 1, the series, the whole series un is convergent, If x is less than 1, it is divergent when x is greater than 1. Test fails at x equal to 1. Now put the value of x equal to 1 in the series here. So what will happen? It will comes out the series as 1 into 2 plus of 1 into 3 into 4 plus of 1 into 5 into 6 plus and so on. So it can be written as 1 divided by 2n minus 1 into 2n. So that will be the series, and if you find out the limit value of this, so limit n tends to infinity, the whole series un is going to be 1, which is not equal to 0. That means obviously this series is not convergent. So this series is divergent at x equal to 1. So we can conclude not only this, but we can conclude that the whole series un is convergent if x is less than 1 and divergent if x is greater than or equal to 1. So this is the theorem, right? The next question is test the convergence of the series 1 plus x by 2 plus x square by 5 plus of xn divided by n square plus 1 and so on. So here un is given, un is xn divided by n square plus 1. Now un plus 1 is so I will calculate limit n tends to infinity, the ratio un plus 1 by un, that is equal to limit n tends to infinity x to the power n plus 1 divided by n plus 1 ka whole square plus 1, right, and into x to n square plus 1 divided by x to the power n. These two terms will give you x. So limit of n tends to infinity x into n square plus 1 divided by n plus 1 ka whole square plus 1, right, and this will makes you 1 only. This will makes you 1. Why? Because it's contain n square plus 1 and here it's also contain n square plus some numbers, right. So that's why this is 1. So this will comes out to be x. So by using the D'Alembert ratio test, the series is convergent if x is less than 1 and diverges if x is greater than 1, and test fail when x equal to 1. Now put those value here and find out that whether this series is divergent and so. So putting the value of x equal to 1 here, the series itself become 1 plus 1 by 2 plus 1 by 5 plus of so on 1 by n square plus 1 plus and so on. So what is the un? Un now become 1 by n square plus 1. So taking limit of un that is equal to 1 divided by n square plus 1. So what is the value of 1 divided by n square plus 1 as n tends to infinity? Obviously it's going to be 0. So that means the series is converging at x equal to 1. So henceforth I can write this one, the series un is convergent. X is less than 1 as well as x is equal to 1, and divergent if x is greater than 1. This is the solution of this problem. Look at the next problem. 1 plus 1 by 3 plus 1 by 9 plus 1 by 3n. So un is given, un is 1 by 3n. So un plus 1 is 1 plus 3n plus 1. So un plus 1 divided by un, taking the limit n tends to infinity, this will gives you 3 pi power n divided by 3 pi power n plus 1 limiting. So this will n tends to infinity. This will give you limit of n tends to infinity 1 by 3. So this is 1 by 3. 1 by 3 is less than 1. So the series is convergent. The series is convergent itself. The next problem, nth term of that series is given. So un is given as 2 by 3 pi power n. Calculate un plus 1, un clause equal to 2 by 3 pi power n plus 1. Calculate limit n tends to infinity. The ratio of un plus 1 and un, this will gives you how much? This will give you 2 by 3. And 2 by 3 is also less than 1. That means this series is going to be a convergent series. This series is going to be convergent series. And how we conclude? We conclude using the D'Alembert ratio test. So I believe that this test, D'Alembert ratio test, is the basic one. You have to start if the term of the series does not containing power and surds and so on, right? Once you start it, this is the basic one. If the test gives you un plus 1 and un as a limiting value, then you use directly and just calculate limit n tends to infinity un plus 1 by un. That means you are going to calculate the limiting value of the ratio of the consecutive terms of a given series, and the whole series, the divergence, convergence and oscillations are not converging, totally depends on the limiting value. If that limit is less than 1, the series is going to be convergent. If the limit is greater than 1, the series is not convergent, so that is divergent. And if limit becomes 1, there is a test fails and we need a higher test. We call it Rabat test. So in the next lecture I will explore Rabat test, and that will gives you the idea where to use the ratio test and when to use the Rabat test, right? So in the next class we will follow the Rabat test. Thank you so much.